Hey everybody, Jake here coming at you with another math lesson, doing it live again this week. I know I've taken a few weeks off of live streaming because I wanted to get kind of caught up on some backlog videos that I had, so I spent the time doing that instead, but we're back at it this week. Hopefully everybody's week is off to a good start, and hopefully you have some questions to go over. As always with these live streams, if you do have any questions, feel free to throw them in the live chat. Even if they're off topic, I'm happy to help address any off-topic questions too if I can. If I can't answer them live, maybe I'll make a video out of your question and post it later on. So any questions you have, just throw them in the live chat as we go along at any point here. But today we're going to be going over some implicit differentiation examples. I'm going to be showing you basically the process that you can use for any implicit differentiation problem, just kind of the simplest way to think about it, basically. There really is just kind of one main thing that you want to keep in mind as you do an implicit differentiation problem. And I'm going to show you what that thing is, because if you do keep that in your mind as you work through these problems, they're going to be a million times easier for you. So let's just go ahead and get started here with a few examples. Implicit differentiation, real quick, actually, before I jump into this first problem, is one of the topics on my free Calculus 1 study guide and in my complete Calculus 1 package. If you want to check those out, there is a link down in the description below. And if you're not watching this live, I will come and put it in the pinned comment as well. So go check those things out. They should be huge helps to you as you go through calculus. But let's go ahead and jump into this first example here. So first of all, we're going to find dy dx by implicit differentiation. And we are given this equation here, x cubed plus y cubed equals 1. So really, when you're doing an implicit differentiation problem, there's one thing that you want to start by looking at, and that is what it tells you to find. In this case, we have dy dx. So the fact that we're finding dy dx, that actually tells us some valuable information just off of that. Whenever you have d something over d something like we have here, whatever is this top letter right here, that's always going to be your function, basically. So wherever you see a y in this equation, we need to treat that as a function. And whenever you see whatever letter is down on bottom, that's what you're going to treat as a variable. So in this case, x, the thing that we have down here on the bottom, is going to be a variable. Okay, so essentially what we need to do is we're going to take the derivative of our variable of both sides of this equation. And as we do that, we need to treat x as a variable and y as a function. Really, all that means is whenever you're taking the derivative of a function with respect to a variable, you want to keep in mind that that function, in this case y, is a function of x. So what that means is like this term right here, for example, and actually, you know what, I'll come back to that a little bit later. First, let's just start with our first step, which is going to be the first step of any implicit differentiation problem, to just take the derivative of both sides with respect to whatever your variable is. So in this case, x is our variable. We're going to take, I don't know why this feels a little off here. I keep writing in the wrong spot. Whatever your variable is, you're going to take the derivative of both sides with respect to that. So in this case, the derivative with respect to x of both sides of our equation. So all you really have to do is kind of break it down term by term. So first of all, this first term here, the derivative of x cubed, since this only has an x in it, it doesn't have any y's in it, it's just x, it's just your variable. When we take the derivative of something with only x's in it with respect to x, it's going to behave exactly the way you would expect. So in this case, x cubed, we can just use the power rule. Power rule says we're just going to bring our power down in front, keep our x as x, and lower the power by 1. So we're just going to have 3x squared for this term right here. Then when we take the derivative of y cubed with respect to x, this is where the kind of one really important implicit differentiation trick has to come into play. And that is whenever you're taking y that has something else being done to it, in this case it's y cubed, that right there tells you you're going to have to do chain rule, because y is a function of x. So really what you should do is think of y cubed is the same as saying some function of x cubed. So if you had some function of x all raised up to the third power, you would have to use chain rule, right? Where you would treat the f of x as your inside function, the cubed piece as your outside function, and you would apply the chain rule from there. So that's what we have to do here too. We have to treat y as some function, and that whole function is being cubed. So when we think about chain rule, we want to think of basically what is our inside function and what is our outside function. Well, like I said, our inside function is going to be y. That's kind of inside this power, basically. And then our outside function is the cubed piece. So the y is the inside function, and then the cubed piece is our outside function. So what that means is chain rule says we take the derivative of the outside, leave the inside alone. So basically, if you have something cubed, you're just going to use power rule. You're going to bring the 3 down in front, leave the inside alone, leave our y as y, and then lower the power by 1. Okay? And then chain rule says the next step is to then multiply that by the derivative of your inside function. Well, whenever you're taking the derivative of your function, your y in this case, with respect to your variable x, you don't really know what the derivative of y is because we don't really know what y is. That's why we're using implicit differentiation, because we don't have an explicit function for y. If we had an explicit function for y, we probably could just use normal differentiation tactics, power rule, chain rule, product rule, all that kind of stuff. Since we don't have an explicit function for y, it is implicit. It's like implied, basically, of what y has to be in order for this equation to work out. This example specifically, we probably could solve for y, but the idea here is that we are using implicit differentiation to get practice with implicit differentiation. Typically you're not going to be able to explicitly solve for y and get a function for it, which the next couple examples we're going to go into are that way. But the point remains that what we need to do is multiply this by the derivative of y. Since we don't know y, we can't know the derivative of y. So really all we can do is to say the derivative of y is just the derivative of y with respect to x, dy dx. Okay. So that's the derivative of this term here. Then we need to also take the derivative of the other side of our equation. The derivative of a constant is just 0. So now that we've taken the derivative of both sides of our equation, now what we need to do is basically move all of our terms with dy dx over to one side of the equation, move all of our terms that don't have dy dx to the other side of the equation, and then that will help us to basically isolate the dy dx. So in this case, we have this term right here that does not have dy dx, this term right here that does. So we can move this term over to the other side by simply minusing 3x squared from both sides. So that's going to cancel this term here, and we're just going to get 3y squared dy dx equals negative 3x squared. And then we can just divide the 3y squared to both sides of the equation, and that'll cancel it on the left. It'll cancel the 3's over here, so we would just be left with dy dx equals negative x squared over y squared. There's no more simplifying, nothing else can cancel here, so that's going to be our final answer in this case. All right. So that is going to be it for this question. If you did get some value out of that, it would be a huge help to me if you could go ahead and hit that like button down below, so I can keep making more live streams like this, keep making more videos like this, keep, crushing calc together all term. I'm not seeing any questions in the live chat, so we'll go ahead and keep on moving on to the next example here. As always, if you do have questions, just throw them in the live chat, and I'll do my best to help answer them. So here's the second example we're going to go into here. Find dy dx by implicit differentiation, where this time our equation that we have is y to the 5th plus x squared times y cubed equals 1 plus y times e to the x squared. So this equation is quite a bit more complex than the first example we went into. I am going to go through it a little bit quicker just because I went into quite a bit more detail about, function and variable and all that stuff going over the first example. If you want to go back and rewatch that, feel free to do so. Real quick, I'm just going to kind of point out, again, we have y is our function. So whenever we have a term that has y in it, we have to be sure to treat that as a function of x, and x is our variable. Okay, so let's go ahead and get into how we actually take the derivative of both sides of this equation with respect to x. So first, we'll just go term by term. Basically, whenever you have pluses or minuses, you split it up there, basically. So in this case, we have one term here, one term here, one term here, and one term here. So first term, y to the fifth. Again, we have to do chain rule here because y is a function of x. We cannot just use the power rule here. We have to treat y as our inside function and then the fifth power portion as our outside function. So chain rule says that the derivative of one function plugged into another function, like we have here, is going to be the derivative of the outside function. So the derivative of the fifth power piece, we'll bring the 5 down in front, leave our inside function as our inside function, leave our y as y, and then subtract 1 from the power. And then we multiply by the derivative of our inside function. The derivative of y with respect to x is just dy dx. Okay. Now this next term here, we're going to have to actually use the product rule. So product rule says that we take basically, let's actually kind of make like a little side problem out of this. We'll say this is one of our functions, this is our other function. So these two things are being multiplied together here. So we'll say basically x squared is f and then y cubed is g. So then we need to find y prime, or f prime, I'm sorry, and g prime. So f prime, derivative of x squared with respect to x, that's just power rule. You bring the 2 down in front, keep the x as x, lower the power by 1, 2 minus 1 is 1. The derivative of y cubed, very similar to how we just did this one over here. We're going to bring our 3 down in front, leave our inside function as our inside function, lower the power by 1, and then multiply by the derivative of our inside function, which is y, which is dy dx. So that was kind of a mixture of product rule and chain rule kind of combined into one thing to find this derivative. Okay. So then what we need to do is we do f times g prime. So we do x squared times 3y squared dy dx. And then g times f prime. So 2x times y cubed. So now this is the derivative of this whole term right here, x squared times y cubed. Okay. And then on the other side of our equation, we have a constant. So we have equals. The derivative of a constant is always 0. So that's just going to be 0. And then to find the derivative of this term here, let's go ahead and kind of break that up into a few pieces as well. Because again, we're going to have product rule and chain rule required to find the derivative here. Because we have the product of these two pieces here, right? So y is one piece and e to the x squared is one piece. Let's just call that f and that g. We need to then find f prime and g prime. So now this is the prior piece. We'll keep that separate. So f prime is just the derivative of your f, which the derivative of y with respect to x is dy dx. Okay. And then g prime is the derivative of this piece here, e to the x squared. Well, e to the x squared is kind of interesting because it actually requires the use of the chain rule twice. We have to use chain rule twice to find the derivative of e to the x squared because we have basically an innermost function and then kind of like a medium inner function and then an outermost function. Actually, sorry, that's not quite right. Nope, we do not have to do that. I'm sorry. I'm overcomplicating it. Okay, so e to the x squared is just going to require chain rule once. We're having to use chain rule within the product rule here. So it's really not too different from what we had to do here. If if instead of e to the x squared, we had e to the y squared, we would have to use chain rule twice because y would be an innermost function within itself. Since we have x squared, though, what we can do is we can treat x squared as our inner function and then the exponential function as our outer function. So we would take the derivative of the outer function, leave the inside function alone, while the derivative of the exponential function, e to the x, is just e to the x. So the derivative of e to the x squared, if we're leaving our inside function alone, just taking the derivative of the outside function, we still have e to the x squared, okay? And then what we have to do is multiply that by the derivative of the inside function, the derivative of x squared. The derivative of x squared is just 2x. So that's going to be our g prime. So now for this overall derivative of this whole thing here using the product rule, we're going to get f times g prime. So y times e to the x squared times 2x. Plus g times f prime. So e to the x squared times dy dx. Okay, so now we have taken the derivative of both sides of our equation with respect to x. So now, same process that we always want to go through with these implicit differentiation problems. Once you've taken the derivative of both sides of your equation with respect to whatever your variable is, in this case, since we had dx on the bottom, we knew it was x. Once you do that, you want to move all of your dy dx terms to one side of the equation, all of your non-dy dx terms to the other side, and then we can go from there. So let's just mark real quick. Our dy dx terms are right here, right here, right here. Okay, so those are going to need to be on one side of our equation. And our non-dy dx terms are here and here. Here we have a plus 0. That doesn't really do anything, so we'll just get rid of that. So we need to move this term over to that side of the equation. And then we need to move this term over to the other side of the equation, to the left side. So first thing we will do is minus 2xy cubed from both sides. Okay, and then we will minus e to the x squared times dy dx from both sides. Whoops, that's supposed to be an e right there. Sorry. Okay, so that will cancel with that. This will cancel with this. So what we will be left with at that point, we're going to have a 5y to the fourth dy dx plus 3x squared y squared dy dx minus e to the x squared dy dx and that's everything on the left side. And then on the right side, we're going to have 2xy e to the x squared and minus 2xy cubed. Okay, and I think that should account for all of our terms here. So once you've gotten all your dy dx terms on one side of your equation and all of your non-dy dx terms on the other side, from there what you want to do is factor out the dy dx from all of your terms that have the dy dx on that one side of the equation. So we're going to basically factor out dy dx from all three of these terms on the left side. So if we take the dy dx out of this term, we'll be left with 5y to the fourth. If we take the dy dx out of this term, we will be left with plus 3x squared y squared. And then if we take the dy dx out of this term, we'll be left with minus e to the x squared. Okay. The non-dy dx side of the equation is not going to be impacted by that because all we've done is factor something out of one side of our equation. And the reason we wanted to do that is now look what happens. Look at where we are at this step here. This is kind of the whole point of wanting to move all our dy dx terms to one side of the equation. And again, that is always what you want to try and do when you're doing an implicit differentiation problem. Because now, notice something very interesting about this step of the process. There's only a single dy dx term left in this equation. There's no other ones anywhere else in our equation. Basically, what we've done is we've consolidated all of our dy dx terms down into one single dy dx. And the reason why that's so nice is if you have dy dx times a bunch of stuff, and that's the entire left side of your equation, what can you do to get the dy dx all by itself so that it's solved for? You can simply divide both sides of your equation by all the stuff within the brackets here. And then that will cancel. I'm not going to write that all out again, but that will cancel with this whole thing here. And then you'll just be left with dy dx equals everything on the right side of your equation all over everything that was within the brackets here. And then that's going to be it. We've solved for our dy dx at that point. And like I said, that's exactly how these implicit differentiation problems are almost always. I don't like to ever say always because you never know what you might get, but almost always going to go. Like that's going to be the strategy that you want to try and apply because it's really going to help you a lot. It's going to make things so much easier for you 99% of the time. All right, I'm still not seeing any questions in the live chat, so we'll keep on rolling here. Got another example for you that we're going to go over. Same idea as we've been doing. We're going to find dy dx by implicit differentiation. This time the equation we have is tan of x minus y equals y over 1 plus x squared. So again, same as these always start. All you got to do to start out is take the derivative of both sides of your equation with respect to x. In this case, whatever your variable is, whatever this letter is down here on the bottom of your dy dx. So we're taking the derivative with respect to x. To take the derivative of tan of x minus y, we're going to have to use chain rule. Chain rule says first figure out what your inside function is. In this case, it's quite clearly what's inside of our parentheses here, and then we can treat the rest, the tan part, as our outside function. So we're going to take the derivative of the outside, leave the inside function alone. The derivative of tan x is 1 over cosine squared x. So in general, the derivative of tan x is 1 over cosine squared x. And this formula is actually on my free Calculus 1 study guide. If you want to go grab that, there is a link down in the description and the pinned comment below where you can go get yourself a copy of that instantly. It is free and it's available for instant download. So go grab that. This is one of the formulas on there. I'm not going to show you in this video how to actually find that derivative, but it involves quotient rule. I'll tell you that much if you want to do it on your own. But for now, let's go ahead and just use this formula. So derivative of the outside, leave the inside function alone. So the derivative of our tan function, leave x minus y as our inside function. So the derivative of the tangent piece is going to give us 1 over cosine squared of whatever our inside function is. So in this case, we're going to have 1 over cosine squared of x minus y, because we need to, by the chain rule, leave our inside function as our inside function. And then we multiply that by the derivative of our inside function, the derivative of x minus y. The derivative of x is just going to be 1 because we're taking the derivative of x with respect to x. X is a variable. We're taking the derivative with respect to x. It's going to behave the way you'd expect. It's just 1. Then to find the derivative of y, y is a function of x. So we don't know what y is. Therefore, we don't know what the derivative of y is. But we can just say minus dy dx. So that's going to be the chain rule applied right there. Then over here, we're going to need to apply the quotient rule. So quotient rule says that the derivative of a fraction like this, basically you want to call the top of your fraction the high part and the bottom of your fraction the low part, higher and lower. The derivative of this, so y is going to be our high, 1 plus x squared is going to be our low. Let's just quickly figure out what the derivative of each of those things are. So basically high prime and low prime. The derivative of this top function, the derivative of y with respect to x, is just dy dx. The derivative of this bottom function with respect to x is just going to be 1 plus 2x. And that would just be with the power rule. I'm sorry, not 1 plus 2x, my bad. Derivative of a constant is always 0. The derivative of 1 is 0. The derivative of x squared is 2x. Okay. So then quotient rule says the derivative of your fraction is always going to be low d high minus high d low all over low squared. So low d high would be low d high, so times the derivative of high. High prime is the same as d high. Derivative of high is dy dx minus high d low, so minus y, times the derivative of low, so times 2x, all over low squared, all over the bottom squared, so all over 1 plus, my goodness, all over 1 plus x squared, all squared. And it is very important when you're squaring this denominator, make sure you have this in parentheses here. The squared needs to be applied to both these terms. And it does not distribute. Remember, that's not how two terms being added within parentheses raised up to a power works. We need to FOIL that out. But I'll get to that in a second. Okay, so like we've been doing, like I've been saying, once you take the derivative of both sides of your equation, what you're going to need to do is move all of your dy dx terms to one side of your equation, move all of your non-dy dx terms to the other side, and then we'll hopefully be able to factor from there. In this case, though, this is a little complicated of a point where we're at here because we have these fractions here, right? So what we probably want to do first in order to be able to effectively move terms around by just simply adding and subtracting them, we're probably going to want to get rid of the fractions, which means we can basically multiply both sides of our equation by the denominators. So multiply both sides by 1 plus x squared squared. And also multiply both sides by cosine squared of x minus y. So I'm kind of out of room to write that, but be sure that you apply both of those. We're going to multiply both sides of our equation by both denominators. And all that really does, another way you could think of it is cross multiplying. So we're going to multiply our denominators across and our numerators across. So we get the denominator over here times the numerator over here. The denominator here times the numerator here, which is 1 minus dy dx. Okay. Now, when we're multiplying our cosine squared x minus y times this whole numerator, notice we have addition and subtraction within here. Make sure you put the whole numerator in parentheses. That's very important, or else you're not going to properly distribute that. And you'll end up with the wrong answer. Instead of y times 2x, I'm going to write that as 2xy. Okay, so now that we've done that, we should be able to kind of expand everything out. So basically kind of distribute everything within the parentheses here, which might get kind of messy. And I'm thinking there's probably going to be an easier way to do this here. Although we might not have that. Yeah, maybe not right away. So let's kind of take this step by step. I'm not going to go ahead and expand everything out all at once. What I'm going to do instead is noticing that there's kind of like this 1 plus x squared term on both sides of our equation. I'm hoping that that might end up simplifying or canceling a little bit. So I'm not going I'm going to keep the 1 plus x squared in parentheses as its own thing here. I'm not going to distribute that out. However, what we will need to do is distribute basically this parenthesis term here into this parentheses. So we're going to get 1 times 1 plus x squared squared, which is just 1 plus x squared squared, and then minus that term times dy dx. Okay. And then over on this side of our equation, we need to distribute the cosine squared term into the parentheses here. So that's going to give us, and this is going to be quite a long thing here. Okay, so what I'm going to have to do is move this over real quick. Okay. So we're going to get cosine squared of x minus y times 1 plus x squared times dy dx. And cosine squared of x minus y times negative 2xy. So minus 2xy cosine squared of x minus y. Okay, so now again, what we need to do, now we've at least gotten it to a point where if we kind of break down all of the terms that we have here, one term there, one term there, one term there, and one term there, we've at least gotten it to a point where we can add or subtract, or I'm sorry, not add or subtract. Yes. So we can add or subtract all of our dy dx terms to one side of our equation, all of our non-dy dx terms to the other side. So I'm going to go ahead and subtract, or I'm sorry, add this term right here to both sides of our equation. To move all of our dy dx terms over to the right side of our equation. So that will cancel there. And then I'm going to add this non-dy dx term to both sides of our equation to move it over to the left side. Okay, and that's going to cancel this here. So we're going to be left with 1 plus x squared, all squared in parentheses, plus 2xy cosine squared x minus y equals cosine squared x minus y times 1 plus x squared dy dx plus this term right here. So plus 1 plus x squared, all squared, dy dx. Okay, so now we've got all of our dy dx terms on the right side of the equation, all of our non-dy dx terms over on the left side of the equation. And if you are getting some value out of this video, do me a huge favor and hit that like button down below. Helps me really, get more traffic on my channel, and so I can keep making more videos like this for you. So if you do find this helpful, that would be a huge help to me as well. But now that we've gotten our dy dx terms on the right side, our non-dy dx terms on the left side, what we can do is factor out the dy dx from both of these terms on the right side, right? There's one term right there. There's one term right there. Both of them have dy dx times a bunch of stuff, right? So we can factor out the dy dx from each of those terms. And what I'm going to do here actually is just kind of color coordinate things just to make it a little easier to hopefully read this. So dy dx is going to be pulled out of both of these terms. If we take the dy dx out of this first term, we're going to be left with cosine squared of x minus y times 1 plus x squared. And then on this term here, if we take dy dx out, we're going to have 1 plus x squared all squared plus 1 plus x squared all squared. Okay. Left side of our equation is not going to be impacted. I don't think that's going to work. I didn't write it straight. Okay, and then once we've got just one single dy dx, right, again, this process worked perfectly again. It was obviously a bit more complicated of an example, but now notice where we are right here, we only have one single dy dx times a whole bunch of stuff in parentheses. So again, super convenient. All we have to do is divide both sides of the equation by everything within these parentheses here. And doing that is just going to give us dy dx equals this whole left side of the equation divided by everything within the parentheses here. And that's going to be it. That's going to be our final dy dx, final solution there. So again, if you've got some value out of this, do me a huge favor, please, and hit that like button down below. Implicit differentiation is covered more on my free Calculus 1 study guide and my complete Calculus 1 package. Links to both those things are down in the description and the pinned comment below. I'm not seeing any other questions in the live chat here, so we'll go ahead and wrap things up. Hopefully you're feeling a bit better about implicit differentiation now, and hope to see you next Monday night for the next live stream. Thanks, and see you next time.